The prediction of the molecular geometry of boron trifluoride using the VSEPR theory, valence shell electron pair repulsion theory, and we draw the Lewis structure first. Boron is found in the third group and second period of the periodic table. Boron has got 3 valence electrons that can be used in covalent bond formation. The fluorine atom is found in the 7th group and also in the second period of the periodic table. Fluorine therefore has got 7 valence electrons that will be used in covalent bond formation. Boron, 3 electrons. The fluorine's 7 valence electrons. This is one example where we cannot form an electron octet around the central atom. This is an exception to the octet rule, and the chemistry of boron trifluoride is represented by this lack of electron octet. Boron trifluoride is a Lewis acid, which implies that another atom or molecule can donate electrons to this open orbital around boron to try and form electron octet. We have got the central atom A, boron now represented by A, 3 terminal atoms. The electron pair geometry will be the same as the molecular geometry. We haven't got any lone pairs around the central atom. Electron pair geometry AB3 will predict a trigonal planar geometry with bond angles of 120 degrees. So that if we predict the molecular geometry now, we use Cooper or Cowper structures. We have got the central atom boron, and in 3-dimensional space we try to draw the correct molecular geometry. Although we introduce the lone pairs on the terminal atoms, we must realize that these lone pairs will not influence molecular geometry. The bond angle here 120 degrees. Trigonal planar molecular geometry. When looking at the structure, it is necessary to realize that molecular geometry is determined by the presence of the nuclei in 3-dimensional space. So fluorine atom nucleus, boron atom nucleus, fluorine atom nucleus, fluorine atom nucleus. Trigonal planar structure, perfect bond angle of 120 degrees. The prediction of the molecular geometry of formaldehyde using the VSEPR theory. VSEPR, VSEPR, valence shell electron pair repulsion theory, and we draw the Lewis structure first. The carbon is the central atom. Carbon is found in the 4th group and second period of the periodic table. Carbon has got 4 valence electrons that can be used in covalent bond formation. Carbon can form either single, double or triple bonds and will generally form an electron octet. The oxygen atom is found in the 6th group and second period of the periodic table and will have 6 valence electrons that can be used for bond formation. Generally though, oxygen will form either single or double bonds and will have some lone pairs. Hydrogen is found in the 1st group, first period, having 1 electron, will always form a single bond and will always be a terminal atom. The central carbon atom has got 4 valence electrons, and we form electron octets around the oxygen atom, but only 2 electrons around the hydrogen. We see that we've got a central atom A bonded to 3 terminal atoms. We haven't got any distortions, but for the fact that we have got a double bond. The double bond will cause some distortion in the molecule because the volume of a double bond is larger than the volume of a single bond. And we do expect, when we start to think in terms of bond angles, that the bond angle from the double bond to the single bond will be a bit larger, and then the bond between the single bond here will be a bit smaller. But nevertheless, electron pair geometry will be the same, AB3, and the electron pair geometry AB3 will predict a trigonal planar structure. For a trigonal planar structure, the perfect bond angle will be 120 degrees. When we draw the molecular geometry, we make use of Cooper or Cowper structures. We have got a double bond to the oxygen, single bond to the hydrogen, single bond to the hydrogen. If we now predict bond angles, we predict this bond angle to be a bit larger than 120 degrees, and this bond angle here to be a bit smaller than 120 degrees. What do we measure in the laboratory? In the laboratory, we measure this bond angle to be 121 degrees and this bond angle to be 118 degrees. The structure trigonal planar. And generally, when we look at the structure of a molecule, it is necessary to realize that molecular geometry depends on the positions of atomic nuclei in three-dimensional space. And when we look at the molecular geometry of the molecule, we move from the hydrogen nuclei to the central carbon to the oxygen. And we will not have the perfect trigonal planar structure. We will have a slight distortion because of the presence of a double bond, and double bonds contain 4 electrons, giving a larger negative space. The prediction of the molecular geometry of the nitrate ion using the VSEPR theory, valence shell electron pair repulsion theory, and we draw the Lewis structure first. Nitrogen, the central atom, is found in the 5th group and 2nd period of the periodic table. Nitrogen will therefore have 5 valence electrons that can be used in covalent bond formation. Oxygen here, the terminal atom, is found in the 6th group and 2nd period of the periodic table, and will therefore have 6 valence electrons to be used in covalent bond formation. The nitrate ion contains an extra electron. This extra electron is accommodated on the more electronegative atom, and therefore one of the oxygen atoms will carry 7 valence electrons. The other 2 oxygen atoms will carry 6 valence electrons. By choice, we write the oxygen atom to the right now with 7 valence electrons. The other 2 oxygen atoms, 6 valence electrons, and we try to form electron octets around each of these nuclei. It is possible, when we use a dative covalent bond, to form an electron octet around the oxygen, so that we can propose a Lewis structure where we introduce one dative covalent bond in the structure, one double bond in the structure, and an ordinary single bond in the structure. It is also possible to write for this molecular structure a resonance structure, where we place the double bond to the right and we accommodate the extra electron on the oxygen here on the oxygen to the left, and we write a dative covalent bond or coordinate covalent bond to this oxygen atom here. We can continue writing resonance structures where we introduce the double bond perhaps to this oxygen here, And what we must understand now is that the real structure of the nitrate ion is the average of all these resonance structures. Because it is an average, it will imply that we haven't got a definite single bond or a definite double bond in one of these positions. We have got something that average out. We will have bonds that are exactly equivalent. They will neither be pure single bonds, neither will they be double bonds. It will be something in between. But it is very important to understand that these bonds are exactly equivalent, and therefore there will be no distortions in this molecule. We look now at a molecular geometry of a central atom A, where A represents the nitrogen atom, and 3 terminal atoms. We haven't got any lone pairs on the central atom, therefore there will be no distortions. Molecular geometry AB3 will come from electron pair geometry AB3, and electron pair geometry AB3 will predict a trigonal planar geometry. Because there are no distortions in the molecule, we predict a bond angle of 120 degrees. When we write the molecular geometry of the nitrate ion, we make use of Cooper or Cowper structures. Nitrogen bonded with a double bond to one oxygen atom with a dative covalent or coordinate covalent bond to the oxygen to the top, and with an ordinary single bond to the oxygen to the right. The lone pairs on the terminal atoms will not influence the structure. We can illustrate the correct structure by writing different resonance structures. Illustrating again the presence of the dative or coordinate covalent bond. So that we have got a trigonal planar molecular geometry, and the bond angles will be all the same. They will all be 120 degrees. When we look at the molecular structure, we must realize that molecular structure will depend on the presence of nuclei in three-dimensional space. Therefore, we've got an oxygen atom, nitrogen, oxygen, oxygen. We have got a trigonal planar structure, and we have got a bond angle of 120 degrees to illustrate the effect of the bonds that are exactly equivalent. The prediction of the molecular geometry of nitrogen dioxide using the VSEPR theory, valence shell electron pair repulsion theory, and we draw the Lewis structure first. Nitrogen, the central atom, is found in the 5th group and 2nd period of the periodic table. Oxygen, the terminal atom, is found in the 6th group and 2nd period of the periodic table. Nitrogen will have 5 valence electrons for bond formation. Oxygen will have 6 valence electrons for covalent bond formation. Nitrogen having 5 electrons, oxygen having 6. We can form a bond to the oxygen to the left here by introducing a dative covalent bond or coordinate covalent bond. That means that nitrogen will donate both these electrons to open orbitals around the oxygen atom in an effort to form a covalent bond. What is clear now is that the 2 oxygen atoms will have electron octets, but the nitrogen has got 1 lone electron, has got 7 electrons around it. This is an example of an exception to the octet rule, and nitrogen dioxide is a so-called radical, a very reactive molecule where this lone electron will want to pair with another electron to form a covalent bond. So that when we write the Lewis structure, we write the dative covalent bond, the double bond, one lone electron. It is also possible, of course, to illustrate this molecule with the resonance structure, where instead of writing the double bond to the right, we can now write the dative covalent bond to the right and the double bond to the left. The real structure of nitrogen dioxide will then be an average of these two resonance structures. We do not expect single or double bonds in the molecule. We expect two bonds exactly the same, not exactly single bonds, not exactly double bonds. The molecular geometry then is determined by the central atom A bonded to two terminal atoms having not a lone pair but just one electron. So the electron pair geometry is AB3, and we expect from the electron pair geometry a trigonal planar molecular geometry with bond angles of 120 degrees. In this example, though, we cannot expect a trigonal planar molecular geometry because we have got one lone electron on the central atom. For the prediction of the molecular geometry, we move from nucleus to nucleus, oxygen, nitrogen, oxygen, and we see then we're going to have a bent molecular geometry. This bond angle will not be 120 degrees. And interestingly enough, this bond angle is measured in the laboratory to be 134 degrees. Reason being that the volume of one lone electron is smaller than the volume of one lone electron pair. And that will be smaller than that of a double bond, smaller than that of a single bond, etc. We make use of Cooper or Cowper structures to draw the molecular geometry. Nitrogen, single electron, dative covalent bond, double bond. The lone electron pairs on the terminal atoms will not influence molecular geometry. Nitrogen, single bond, dative covalent now to the right, double bond to the left. Bent molecular geometry, bond angle 134 degrees. The bond lengths are expected to be exactly the same, and they are measured to be 119.7 picometers in the laboratory. So that instead of a trigonal planar structure, we have got a molecule with bent molecular geometry, where we move, when we look at the molecular geometry, from one atomic nucleus to the other atomic nucleus to determine the molecular geometry. The prediction of the molecular geometry of the nitrite ion using the VSEPR theory, valence shell electron pair repulsion theory, and we draw the Lewis structure first. Nitrogen is found in the 5th group and 2nd period of the periodic table and will have 5 valence electrons to form covalent bonds. Oxygen is found in the 6th group and 2nd period of the periodic table and will have 6 valence electrons. The nitrite ion contains an extra electron. The extra electron of the nitrite ion is accommodated on one of the oxygen atoms, the oxygen being more electronegative than the nitrogen atom. So that we have got nitrogen, 5 valence electrons, 1 oxygen with 7 valence electrons, 1 oxygen with 6 valence electrons, brackets, and the charge on the molecule. It is possible to write a resonance structure for this molecule. Instead of placing the extra electron on the oxygen to the right, we can of course place the electron on the oxygen to the left. Then we have got a double bond on the oxygen to the right, and then a single bond on the oxygen to the left. All the atoms in this molecule will have an electron octet. The molecular geometry, we have got a central atom A, nitrogen is represented by A, 2 terminal atoms, and 1 lone pair. The electron pair geometry is AB, and then 2 plus 1 makes 3, AB3, and that will describe the trigonal planar electron pair geometry. For the trigonal planar electron pair geometry, we predict perfect bond angles of 120 degrees. For our molecular geometry now, we realize that instead of 3 terminal atoms, we will have 1 lone pair. When we've got a lone pair, we expect bond angle distortion, and we expect this bond angle to be smaller than 120 degrees. The volume of a lone pair is larger than the volume of a double bond, and that is larger than that of a single bond. We predict now a molecular geometry bent, and we draw the molecular geometry by using Cooper or Cowper structures. In three-dimensional space, we try to represent our compound, our molecule. And we draw both the resonance structures. There is only one structure for this compound, and the average of the 2 resonance structures will describe this compound. We haven't got double bonds and single bonds in our compound. We have got something that is not clearly double bond, not clearly single bond. And when we measure the bond angles in the laboratory, we find this bond angle to be 115.4 degrees, and that both these bonds are exactly the same, and they are 123.6 picometers. The molecular geometry then bent, because the molecular geometry will depend on the presence of the nuclei. We start with an electron pair geometry trigonal planar, but our molecular geometry is bent because we move from nucleus to nucleus to nucleus, and we've got a lone pair on the central atom. The prediction of the molecular geometry of ozone using the VSEPR theory, valence shell electron pair repulsion theory, and we draw the Lewis structure first. Oxygen is found in the 6th group and 2nd period of the periodic table. Oxygen will have 6 valence electrons that can be used for covalent bond formation. Central oxygen, terminal oxygens, and in an effort to write electron octets around the terminal atom to the left, we introduce a dative covalent or a coordinate covalent bond, so that we suggest a Lewis structure where we have got a central atom, one dative covalent or coordinate covalent bond, and one double bond. It is necessary to realize that it is also possible to write a resonance structure for this molecule. The choice was now to write a double bond to the oxygen to the right, but of course we can rather write a dative covalent bond to the oxygen to the right, and then we can write a double bond to the oxygen to the left. What is necessary to understand is that there is only one structure for ozone, and this structure is represented by the average of these two resonance structures. What is clear is that we will have bonds, and these bonds will not be definite single bonds or double bonds. Their nature will be something in between a single and a double bond when we measure the bond lengths. When we want to predict the molecular geometry, we think in terms of a central atom A, which is oxygen, two terminal atoms, also oxygen atoms, and one lone pair. So that the electron pair geometry is AB, and then 2 plus 1 gives 3, AB3. Electron pair geometry AB3 will predict a trigonal planar structure. For the perfect trigonal planar structure, we expect bond angles of 120 degrees. Our molecular structure now will not be the perfect AB3, but will be a distorted molecule because we have got a lone pair on the central atom. The volume of lone pairs in space is larger than the volume of double bonds, larger than single bonds. So we expect the influence of the lone pair to be to decrease this bond angle, and we predict a bond angle that will be smaller than 120 degrees. When we draw the Cooper or Cowper structures, we draw the correct molecular geometry. So we have got a central atom, oxygen, dative covalent, double bond. Very important to introduce your lone pair on the central atom. Well, we introduce the lone pairs also on the terminal atoms, but they will not play a role in determining the molecular geometry. And of course we have got a resonance structure where we have got a central atom, and now the dative covalent to the right, the double bond to the left, lone pair. The structure depends on the presence of the nuclei. When we move from this nucleus to that nucleus to that nucleus, we have got a so-called bent structure. The electron pair geometry will be trigonal planar, but our molecular geometry will be bent. We predict a bond angle of smaller than 120 degrees, and in actual fact, this bond angle is measured in the laboratory to be 116.8 degrees. These two bond lengths are exactly equivalent now, and it has been found to be 127.8 picometers. Looking at the molecular geometry, electron pair geometry, trigonal planar, molecular geometry though, bent. We move from nucleus to nucleus to nucleus to describe the molecular geometry.